Hey team, sorry I'm not here today. I do have a Flashback Friday for you to get us rolling to review for the AP exam in May. So we're going to do a problem that centers around KSP and then a little Le Chatelier's principle as well. So why don't you grab a sheet of paper, do these two problems with me as we go. All right, so let's start with KSP. This problem says that the solubility product constant, KSP, for the reaction is 1.0 times 10 to the negative 6. Remember, KSP is describing the equilibrium position of a very specific type of equation. It's when an ionic solid breaks into the ions. So K is just the equilibrium constant. KSP is the specific type of reaction solid breaking apart. So the first question is, what is the KSP expression for BAF2? So for K, we always do our products divided by our reactants. So here's my first product, Ba2 plus. Here's my second product, so times the concentration of F minus, and that guy's going to be squared because there's 2. Now I would normally do divided by the reactants, but remember, no sneaky solids allowed, so that is my KSP expression right there. Letter B, what is the molar solubility of BAF2 in the saturated solution? So molar solubility is what we define as X in our ICE table. It's telling me how much of that solid is actually going to break apart to reach that equilibrium. So because we're talking equilibrium, let me go down here a little bit. Nope. All right, just kidding. I'm going to take my reaction, BAF2 sneaky solid, breaks apart into Ba2 plus and 2F minus. We're going to do ice, ice, baby. We don't care about the sneaky solid. Because we don't have any to begin, we're going to start with no concentration. I'm going to add some value of X. I'm going to add some value of 2 times X. So we get X and 2X. They told me that KSP is 1.0 times 10 to the negative 6, and now we're just going to plug in that equilibrium line. So I'm going to take X times 2X, and don't forget that this guy was squared, so we got to square that here. So then I get 1.0 times 10 to the negative 6 equals 4X cubed. Don't forget that 2 applies to the 2 and the X, so that's really 4X squared times X, so 4X cubed. And I'm going to solve for X. X is 6.3 times 10 to the negative 3rd mole per liter. So when we solve for X, it needs a unit, either big M for molarity or mole per liter, and that is our molar solubility. We say it's the molar solubility of this solid because really, even though we don't care about the sneaky solid, it's kind of representing what this minus X value is right here. How much of this sneaky solid is actually breaking apart into these ions. So 6.3 times 10 to the negative 3rd moles per 1 liter of water of this sneaky solid is breaking apart. All right, letter C. They want to know, will a certain amount in concentration of NaF and a certain amount in concentration of BaNO3, will there be a precipitate? So first of all, let me figure out what the precipitate would be. If NaF and barium nitrate were to react, I would make sodium nitrate and barium fluoride. Sodium is always going to be aqueous and soluble, so that means BAF must be the solid that they're talking about. So what I'm really asking is, we're going back to our KSP, which is always the solid breaking apart into the ions. Okay, what I'm asking here is, will the reaction shift left? Because if it shifts to the left, that means the precipitate, the solid, will form. So the first thing I need to do is I need to figure out the new concentration of F minus because I have a molarity and I have a volume. So let's do our F minus. We're going to take M1 times V1. We're looking for the new concentration when they mix, and we'll add the total volume, so 500 milliliters plus 400. So when I solve for the new concentration, I get 0.0033 molar. Let's do the same thing with the barium. We have M1, we have V1. So I have starting 0.06 molar. I have 400 mils of this, solving for the M2, and we have 900 total. So I get my M2 value as 0.002677 molar. I'll worry about sig figs at the end. So how do I know if it's going to be precipitate that forms? We're going to use QSP, which is the same expression, the products divided by the reactants, but we have a sneaky solid, so we don't worry about that. So let's just plug in those numbers. QSP is going to be equal to 0.002677 times 0.0033. Don't forget that guy is squared. Oops. All right, almost done. So I get my QSP is equal to, when I plug this into my calculator, 2.94 times 10 to the negative 8th. We're going to compare that to KSP, which was given in the last problem. We used it right here. It's 1.0 times 10 to the negative 6. So QSP is less than KSP. And remember, we always move towards the K. So if KSP is bigger than my QSP, we're going to move to the right. So we shift right. And in this reaction, the right is aqueous, so no precipitate forms. All right, lastly, write the net ionic equation. So we're doing letter D. So this is just working on net ionics. When a solution, that means aqueous, of BaF2 is mixed with a solution, that means aqueous, of K2CO3. So we predict our products. The first metal is going to go with the negative polyatomic. So we got a crisscross. Barium is +2. Carbonate is -2. So those just cancel. Plus my positive metal, potassium, is going to go with my non-metal, fluorine. +1, -1. So those guys cancel. We're going to balance. And we know the alkali metals. Potassium is always aqueous. This guy is going to be my solid. So then if we do my full ion equation, Ba +2 aqueous plus 2F minus aqueous. We only break apart aqueous things, strong acids, strong bases. 2K plus aqueous plus CO3, 2 minus aqueous makes, we leave the solid all together, don't touch it, and then we break this one apart. 2F minus, doing my own order. 2F minus plus 2K plus aqueous. And now we are going to cancel out spectator ions, things that are aqueous on both sides. 2F minus, 2F minus, 2K plus, 2K plus, and we rewrite the entire thing without those spectators. So there's your net ionic equation. All right, this one should go a lot quicker. So we took we have a balanced equation, and we have the equilibrium concentration. So this is our E line of the ice table. Write the expression for Kc. That's easy. So Kc is going to be my products. I have a gas, so that can go in there, squared over another gas and H2 cubed. Notice I'm using molarities instead of partial pressures because they gave me molarities in the problem. If they gave me pressures, then I would do Kp. But they also asked for Kc. All right, so now we want to calculate. So all I need to do is plug in my equilibrium values. And K does not have a unit, so Kc in this case is equal to 10. Because it's bigger than 1, that means my product is favored at equilibrium. All right, now a little bit of Le Chatlier. So these are stresses to the system, and it's going to cause the reaction to shift in one direction or the other. And I want to know, how will H2 be impacted by this? So how will this guy right here be influenced? So first of all, the temperature increases. Well, I can see that this is negative, so it is exothermic. That means heat is released, so we can add heat as a product. If I jack up the temperature, my product side is getting an increase, so the overall reaction is going to shift left. And what I care about is this H2. It is on the left side, so the concentration of H2 will increase if we shift towards the side of H2. Now, what if I add N2? So I'm adding some of my reactant. That means we are going to shift towards the product side, so we are going to shift right. and that's away from where H2 is, so that means the concentration of H2 will go down as a result. So there's a little bit of equilibrium and a little bit of Le Chatelier's.